My name is Roland Hotchkiss. I'm a professor of civil engineering at Brigham Young University. What you are about to see are summaries of a workshop that we participated in this week as part of the MSAC effort to work with the Army Corps of Engineers to develop a management plan for the sedimentation in Lake Lewis and Clark. Each of these videos is presented by a subject matter expert, and I hope you'll agree when you've finished viewing them that they truly are experts in their area. Thank you.
Hello, my name is Paul Boyd. I'm a hydraulic engineer with the Omaha District, U.S. Army Corps of Engineers, and this is a short history of Gavins Point Dam and sedimentation in Lewis and Clark Lake. A summary here of the sponsors of the project. Primarily our lead sponsor is the Missouri Sedimentation Action Coalition, and a thank you to all those partners. A history of construction of Gavins Point Dam. It was authorized as part of what's called the Pick-Sloan Program, more formally known as the Flood Control Act of 1944. It cost $49 million in 1950, and it took approximately 5 years from groundbreaking till it filled and ran at normal capacity in 1957. You see on the right there, then General Pick at the groundbreaking in 1952. A quick summary of how the dam was built. You see in the lower front area of that image there, a dike being built across the Missouri River from the Nebraska to the South Dakota side, pushing the channel to the South Dakota side so that the powerhouse and the spillway could be built in the dry. All of the earth was moved for this project in dump trucks, and by today's standards, very small dump trucks. Thousands and thousands of loads, 40 yards at a time to build the earthen embankment. They cut into Calumet Bluff on the Nebraska side to key in with concrete the powerhouse and the switchyard. And a picture here of once that powerhouse was complete, filling of the reservoir. This is looking downstream. These are the intakes to the powerhouse where there are 3 Kaplan turbines producing about 130 megawatts of power since 1957. Picture of a gentleman on the now the wet side or the reservoir side of the spillway gates for scale. He would be under about 25-30 feet of water at normal lake conditions. You see here the construction of the powerhouse on the lower left and the spillway on the lower right. In 1955, when the embankment was complete, the cofferdam in the upper left was breached and water started to flow through the powerhouse and up against the spillway gates. The closure of the dam was in July of 1954. In the middle of the night, the last loads of material were pushed across on the South Dakota side, and a fairly significant local party broke out the next morning of locals coming out to see the official closure. Since that closure, the dam is operated for 8 authorized project purposes you see listed there. The Corps of Engineers manages the dam and reservoir to maximize as much as possible for all 8 of those purposes, knowing that there are trade-offs to that consideration. So in 1957, we had about 575,000 acre-feet of storage, 132 megawatts of power generation, and a surface area of 29,000 acres. Overall, Lewis and Clark Lake behind Gavins Point Dam is a pretty small piece of the flood storage equation along the main stem Missouri. However, with the influence of sediments from the Niobrara, it does have a relatively high sediment inflow for its volume, making it as a percentage, the most impacted reservoir in the system. And that impact is seen by the formation of a delta, both in the lake and up at the mouth of the Niobrara. The sediments are generally sand that fall out at the headwaters, is the visible delta that most people see when they're up in the Springfield area. In addition, fines settle at the bottom of the reservoir, create a mud layer at the very bottom. So over the past 70 years, that visible delta that everyone sees has moved from about Springfield down approximately another 7 miles into the lake. And without any changes to management or mitigation of sediment inflow, that delta face will continue to move eventually till it approaches the dam itself. So where are the extents of this sedimentation impact that we see? Obviously, they're at the delta location, but that delta also causes a backwater effect that creates additional deposition upstream, all the way well up the Missouri, up the Niobrara River, up Verdigris Creek, in the lake itself, of course, and with the absence of sediments, we do have degradation of the river channel, a cutting down of the river channel for about 50, 60 miles below the dam. So where does this sediment come from? A number of sources, but the large driver is the Niobrara River. And so that would be a significant place to focus efforts to reduce sediment inflow into the reservoir. And it gives us a good indication of what the makeup of the material is in the delta. So how much sediment are we talking about? Well, we in the numbers we use of acre feet, that's a 1 acre area, 1 foot deep. That's about a football field. So an acre foot is about a football field, a foot deep. That equates to about 4.3 million cubic yards of material. And we just made a couple of comparisons here in trucks, 1,200 trucks a day, 214 train cars, or 12 barges. That would be every day, 365 days a year since closure of the dam. And if we were to actively try to remove that sediment for the system, those are just some examples of the sheer volume of material we're looking at. So when we jump forward to the most recent survey, you see there what our numbers were in 1957. And in 2012, we were down to 425,000 acre feet, a loss of 150,000 acre feet. And surface area reduced by 7,000 acre feet. Those are numbers from almost a decade ago. We would expect additional storage loss and surface area lost up to the current condition and the current time. So thank you for your time. Appreciate your interest in the project, and hope you enjoy all the other videos as part of this session.
I'm John Shelley from the Army Corps of Engineers, Kansas City District. I'm a sedimentation engineer. And I'm going to be presenting on one of the ideas that we discussed in our workshop, which is building a sediment trap. And as you see here in the picture, this is a sediment trap on a river downstream from Mount St. Helens, which contributed a lot of sediment after it blew. So the concept is to build something similar, some sort of structure across the major tributaries that contribute sediment to Lewis and Clark Lake, like the Niobrara River. So there would be some sort of structure built across the river, and that would back up sediment. And then you have to periodically clean out the sediment. And one way of doing that would be through just normal excavation, putting it on dump trucks and hauling it away. So if you were to do this on the Niobrara River, how many dump trucks would you need? Well, it turns out you would need about 600 dump trucks per day. And that's about 1 per minute for 10 hours per day, 365 days per year, every day, forever. So there's some advantages and disadvantages to this type of an approach. The main advantage is it keeps the sediment out of the lake. And then it's a pretty common technology. We know how to build sediment traps. We know how to load dump trucks. Disadvantages, of course, would be the cost. To run 600 dump trucks a day would be very expensive. It'd also be very expensive in terms of upgrading roads, etc., to handle that much traffic. And there's other disadvantages as well. Somewhat shifts the impacts from in the delta where the sediment's depositing now to the tributaries, like to the Niobrara River. There'd be maintenance required on, of course, the whole fleet of dump trucks, but also the structure itself, their land costs, and then ultimately this reduces, but it doesn't eliminate the growth of the delta because it wouldn't be trapping all of the sediment coming into the lake. But it could make a big dent in it. One of the big questions that comes out of this is, where do you put an entire lake's worth of sediment? And this would require, really large amounts of land year after year after year, so much that there's really no way you could put it on the land. So the only place you could put the sediment would be in the river channel downstream from the dam. And now there are other variations to this. Instead of trapping and trucking, you could trap and pipe. You could trap and pump it up to a barge that then you float down to the dam. Some of the other ideas that you could use for dredging right out of the lake, you could use for dredging and getting sediment out of a sediment trap area. So there are advantages and disadvantages to this sediment management technique, and it's something that we'll be studying further.
I'm Meg Jonas, hydraulic engineer retired from the Army Corps of Engineers. I'm here to talk about the Watershed Sediment Management Alternative. First, I'd like to say thanks to all our partners, in particular, the Missouri River Sedimentation Action Coalition, who organized this meeting. So the alternative of watershed sediment management is works in the upstream watershed to reduce the incoming load to the reservoir. It involves measures such as stream bank stabilization, grade control, gully stabilization, farm ponds, and upland conservation techniques. It's unlikely that this alternative would be a standalone solution to the problem. However, it could reduce sediment loads coming into the reservoir permanently, and a certain percentage of those, and it's often highly cost-effective and has on-site benefits. So the sediment sources to the upstream, from the watershed upstream, if you look at this graph, 50% of the incoming sediment load comes from the Niobrara River Basin. That's almost entirely fine sand, and it contributes to the delta formation, both at the Niobrara and the delta at the upstream end of the reservoir, which have sort of merged. The other components of the watershed sediment load have more fine material and probably some coarser material. They're not as uniform as the load from the Niobrara. And the two adjacent creeks to the basins to the Niobrara, Ponca Creek and Brazil Creek, have the same geology as the Niobrara and the same sediment loads. So the Niobrara Basin would be the ideal candidate for addressing the incoming sediment load with any kind of watershed sediment management. So here's a typical stream for discussion. This is not in our basin, it's just a good picture. But if you look at this channel and assume that it's stable, it's a gravel bed stream with some coarse sand in the bed, and it's got eroding banks. Now, if the channel is adjusted to that load of material from the eroding banks, then we need to be careful in our progress with bank stabilization. But let's just say we want to stabilize the eroding bank here, and that material is very fine. Imagine it's almost like talcum powder. Well, when it erodes, it doesn't interact with the bed at all. So I can stabilize the bank line, and the bed of the channel doesn't even know that sediment's there. However, if you imagine that bank, as it occurs in the Niobrara, is almost entirely the same material that's found in the bed of the channel, then the channel is adjusted. It's at equilibrium with that incoming sediment load. And if I stabilize the bank and cut off that sediment load, I'll create hungry water. The stream will pick up, when the load is cut off, it will pick up additional material off the bed of the channel and degrade or in size, it downcut. So those are sort of the two mechanisms that are going on. The other scenario is that I might cut off a supply of sediment that is not in the channel bed at this point, but it may form bars, etc., downstream. So in the Niobrara, we're looking at cutting off sources of sediment that are similar to the bank material in general, or the bed material in general. And when those are cut off, the channel will probably readjust to a new flatter slope, and there may be the potential for incision. So bank stabilization techniques look like this. This is an example from Illinois in a farm field. To the left, there's a picture just after construction. To the right, there's a picture a year later. In the last several decades, we've taken techniques that have been used for quite a while on large rivers such as the Missouri, Mississippi, Arkansas, and we've used them on much smaller streams. They're low cost, effective, and not invasive. You'll notice that the bank there's no grading to the bank. The stones placed entirely in the stream. So these are effective and low cost, and offer good opportunities for cutting off sources of sediment. The advantages and disadvantages of watershed sediment management. We'll talk about the disadvantages first. You need long-term maintenance and subsidies when you look at the upland techniques such as crop tillage, changes in crop tillage. And you also deal with a lot of landowners. The advantages are that it's a relatively low cost per ton of sediment stabilized. There's a potential for permanent reduction in sediment inflow. And there's also on-site benefits, not loss of farmland, loss of topsoil. There's many existing programs that can be utilized, and there's also the potential for improvements in water quality. The time frame of benefits depends on the grain sizes and the transport of the stabilized area. When you stabilize sources that are wash load, the very fine material, those impacts and benefits are felt almost immediately. But in this scenario, the fine material goes to the downstream end of the reservoir, so that doesn't have an impact on the delta. For a reduction in the load to the delta, we'd cut off the supply of sand-sized material, but since that's also the bed material, we would have to adjust the morphology of the channel. That is, adjust it on a flatter slope for that new lower sediment load. And one other scenario is that you can reduce the supply of sand-sized material. If you do that within a grading reach in the Niobrara or Ponca Creek, then that will reduce the aggradation. This solution could be implemented. You'd need data collection, a geomorphic assessment of the watershed and the tributaries, a development of alternatives to see where you get the most bang for the buck in structures, and an evaluation of sediment transport to make sure that you are not destabilizing any reaches by your work. The primary obstacles are funding mechanisms, and this would be an interagency effort. Again, to reiterate, the watershed sediment management alternative has a great deal of benefits to offer as part of an overall comprehensive solution. It is unlikely to be a standalone solution, but it does have value as part of an overall solution.
Hello, my name is Greg Morris. I'm a consultant. I work with reservoir sedimentation problems in many different countries of the world. And I'd just like to talk a little bit about Lewis and Clark Lake today. Lewis and Clark Lake, has a delta that has been advancing for a number of years. And the problem, of course, is that the lake, the delta converts into a Phragmites wetland, which is a low-value wetland. And over time, this reservoir, like all other reservoirs in the world, traps sediment. Normally, the river carries sediment downstream. You build a dam, the dam collects sediment, and we have a management decision. We have to decide whether we're going to manage the reservoir so that we can continue to pass sediment downstream while we retain storage and benefits, or when it fills up, it will then pass sediment downstream. So the idea is to reestablish a sediment balance along the river while still maintaining as many benefits as we can. And the problem, of course, is that the benefits with sediment management aren't the same benefits as we had when the project was brand new. So from the standpoint of management, sediment sluicing is a process that has been used on a number of sites, and it's based on operating the reservoir with a high flow rate with gates open during a short period of time so that you pass sediments downstream. This would work at Lewis and Clark because it's a really small reservoir compared to the annual inflow, and the control of the flow is managed by Fort Randall upstream. So it's possible to flush sediments through this reservoir, particularly the sediment load from the Niobrara River, which is the highest load coming in to this reservoir. If you look at a typical reservoir sedimentation pattern, you get a delta, which is created upstream, and then you have fine sediment, which is deposited downstream close to the dam. And we see this pattern very clear in Gavins Point Dam and Lewis and Clark Lake. And what happens when you do a sluicing operation, you start to scour material from the delta, you move it downstream until eventually you have a new profile running through your reservoir so that during these scouring events you can pass the sediment downstream and therefore come close to achieving a sediment profile. Sluicing only occurs with large flows. It's different from what we typically call flushing, which are typically done with lower flows. Flushing gives you a fairly large, high concentration of sediments downstream. There's a lot of downstream impacts. The idea with sluicing is to pass as much water as possible so you get a dilution impact and you carry the sediments on downstream to minimize downstream impacts. The sluicing will remove some of the material from the existing delta. The delta will convert from multiple channels into having a single deeper channel, but it's not going to remove the delta. The material that's on the delta is pretty much going to stay there, except for this channel that you scour through the delta. The new profile that will form, this is a profile that goes along the channel, and that channel will go all the way to the dam and then start pushing sediments over the dam. It takes some years, maybe a decade, for this channel to extend through the pool and to the face of the dam. And remember, this will occur when the reservoir is at a low level. So there's a graphic that shows approximately what the channel might look like. This is a 1,000-foot wide channel, which is about the same width as the river upstream of the dam, and we could expect the channel to be about the same dimension. But this channel will be submerged when the reservoir is at a normal pool elevation of 1206, 1208. And because the channel is formed and the sediments are passed downstream with the reservoir at a low level, when you refill the reservoir, it's all underwater. So you are that way able to maintain your open water in the lake. So the lake will be drawn down probably about a week of drawdown period, probably 1 or 2 weeks of flowing water through the reservoir at a low level, and then another week to refill. The reservoir is not completely empty because there is a pool behind the dam, even when the sediment flows over the dam, but this channel will actually build up along the right-hand side of the reservoir as it goes towards the spillway at the dam. And if you look at the reservoir typically we look at reservoirs or any hydraulic cross-section using an exaggerated vertical scale. And when you put this vertical scale so that the horizontal and vertical scales are the same, you can see that the spillway is actually a very long way from the marina when you scale these things to true life. So advantages of sluicing, we can maintain open water in the lake. And as I mentioned, the sluicing channel itself will be visible during the drawdown, but when you refill the lake, it's going to be all underwater. we can stop the advance of the delta. We'll export a lot of sand downstream, which will go a long way towards re-achieving the sediment balance along the river between the upstream and the downstream part of the dam. We don't expect it's going to require expensive spillway modifications, and we don't have any large annual cost like you would have if you were dredging. Disadvantages, one big disadvantage is going to be you're going to have a lot of impacts to fisheries. There seems to be no way around that. There are ways to mitigate, but this is something that needs to be researched to figure out what is the best way to mitigate impacts to fisheries. There will also be impacts to water supply intakes, but by the same token, if you don't do anything, the intakes will also be affected by the advancing delta. Hydropower, they'll have some impacts to hydropower, not probably very large. There is no perfect way to manage sediment. Reservoirs were not originally designed to manage sediment. When you manage your sediment, you're going to lose some of the benefits that you've been accustomed to having over the past years and decades. But the other option is to lose all these benefits. So we're trying to figure out how to best reestablish that sediment balance to avoid the reservoir becoming completely filled with sediment, or of course the other option is to eliminate the dam. The best strategy basically is to start working on this today, because to convert reservoirs to a sustained management like this, historically what we've seen in multiple sites over the world is that it takes at least 10 years to go through the process required to begin this process. So start today, look towards the future, and map out a roadmap for sediment management that you can live with for the next 50, 100 years and achieve a sediment balance. Thank you very much.
My name is Tim Welp, and I work at the U.S. Army Corps of Engineers at the Engineer Research and Development Center in Vicksburg, Mississippi. And today I'd like to tell you about the use of dredging as a sediment removal solution in the Lewis and Clark Lake. Now, dredging is a well-established method for removing sediments from reservoirs, and it's actually the most used method in the United States today. It's been used in the past at Lewis and Clark to manage sediment, such as the dredging project in Springfield back in 2014, and depending on specific future project requirements, considerations, and limitations, it could be used in the future as well. But there are a number of environmental, economic, and social aspects that have been identified at this workshop that would have to be resolved first to allow it to provide sediment management solutions on a larger scale in the Lewis and Clark Lake. Advantages of these technologies include that because there are a number of different types and sizes of dredges, that they can be selected to optimize their use to meet specific project requirements. This allows dredging to be optimized and used both in the near and long term. And there's continuing research and development being conducted to improve its use, such as improving productivity, life of pipe, and aspects such as that. This variety of dredging equipment and capabilities allow it to be scalable, up or down, to meet project requirements. And in order to transport sediment, it doesn't require the volume of water that's used to conduct other reservoir sediment management alternatives, such as drawing down the water level in the reservoir to flush sediment out. And the sediment removal results are relatively immediate. And dredging is just another tool in a toolbox. It could also potentially be used to supplement some of the other sediment management alternatives being discussed here at the workshop as well. Disadvantages include that dredging can be expensive. And as identified at this workshop, that funding currently doesn't exist for large-scale dredging projects at Lewis and Clark. Now, there are limited options on where to place any sediment that would be removed from the lake. And as we're learning in the Corps' navigation dredging mission, beneficial use of dredge material is key to sustainability. Now I'd like to talk about factors involved in the selection of dredging equipment as they apply to dredging. The Omaha District, Core District, is currently investigating the selection and sizing, as well as preparing approximate cost estimates on a conceptual basis. The physical characteristics of sediment influence the selection of the type of dredge as well. And in Lewis and Clark, it's predominantly fine sand that ranges in size from about 0.2 to 0.3 millimeter sand. What you're going to do with the dredge sediment, how you place it matters. For the purposes of the conceptual study, the placement of the sediment downstream of the dam back into the river will be used. But obviously, there's a wide variety of uncertainty currently exists about this option, including environmental impacts, effects on infrastructure downstream, and etc. Now, the amount of sediment annually entering the reservoir, it's approximately 3.48 million cubic yards, is being used as the maximum amount that would be possibly placed downstream to maintain the river's natural sediment supply rate. The district is also looking at other quantities of sand to be transported as well. So the dredge site is currently envisioned to be on the western end of the lake on the developing delta, such that there's not an extensive mat of vegetation formed. The extensive vegetation mat will reduce the dredge's production, as well as we do not want to be pumping that extensive amount of vegetation downstream and into the river. And this site would encompass that 3.48 million cubic yards or lesser material. This sediment would be transported down the lake and over the dam in a pipeline. And the pipeline would have two discharge ports downstream of the dam in the river. The first one would be located approximately half a mile downstream, and second port would be a mile downstream to be able to apply the sediment back into the river and to avoid concentration of the sand as it's being introduced into the lake. Basically, there's two types of dredges that are being evaluated. The first type of dredge that's being investigated for use in Lewis Clark is called a cutterhead hydraulic pipeline discharge dredge. This dredge works by a mechanical agitator that the cutterhead that dislodges sediment, feeds it up into a water sediment slurry that is sucked into a centrifugal pump, and it's discharged out the aft of the dredge through a discharge pipeline. This pipeline is envisioned to be deployed along the length of the lake, and due to the longer discharge distances, we'll have to use booster pumps to add additional energy to the slurry to be able to pump that long distance, and currently envisioned about 3 extra booster pumps. And in turn, the discharge pipe will go over the dam and down into those two discharge locations that I talked about. Consideration of this dredge is going to involve a multitude of considerations regarding environmental impacts at the excavation site as well as the placement site, and impacts to recreational boating, and it'd have to be withdrawn every winter just due to the winter conditions. The other type of dredge being investigated is called a mechanical dredge, and this basically consists of a bucket on the end of a stick and a boom that's dipped down into the sediment, comes up with a bucket load, and will be side cast into a barge. These barges, once filled, are transported down to the dam, and the material is placed into a temporary holding or storage area where it will be subsequently dredged by another cutterhead dredge to be pumped through a discharge line up over the dam and into those two discharge ports I previously described. The impact, again, on recreation, the safety to boaters would have to be considered. So what I've done today is explain dredging as a potential alternative for sediment management. It works. It's expensive, but it works. So used in combination with other alternatives, dredging can be an effective alternative for maintaining Lewis and Clark Lake. So whatever dredging technology we select, we have to absolutely ensure that it does not provide a mechanism for Asian carp to migrate upstream over the dam to protect Lewis and Clark. If you'd like to have more information on this sediment management alternative, please feel free to reach out to MSAC.
The ultimate solution is yet to be developed. Next steps include discussing these with the Corps of Engineers and deciding upon a further course of action. MSAC is going to be pushing the Corps of Engineers to put into practice what sustainability truly means. That is, changing the operation of Gavins Point Dam in mind of future generations to extend benefits well beyond the anticipated project period of the dam. We're grateful for the opportunity of working with the Corps and MSAC and hope that these videos have been instructive to you. Thank you.